Hello, everyone. Let me just quickly get set up. All right. I hope everyone can see the screen. Let's just present real quickly. Make it a little bit larger. All right. Well, hi, welcome. My name is Becca Powers, and I am a junior in the College of Arts and Sciences. I am studying chemistry and biomedical physics. And today I'd like to talk to you a little bit about my chemistry research. So I have been researching with Dr. Coyote Oshin for 3 years now, ever since my freshman year. And we focus mainly on catalysis, which is how effective catalysts are in various reactions. So the reaction that we specifically focus on is something called atom transfer radical addition. It is a type of addition reaction where you can add halogens to an alkene, which is a molecule with a carbon-carbon double bond. And atom transfer radical addition reactions are used for a variety of industry purposes. And there is one specific catalyst that works very, very well for these atom transfer radical addition reactions. That catalyst is known as tris-2-pyridylmethylamine. I'm going to call it TPMA for short. And TPMA is used industrially quite a bit to speed up these reactions. And by speeding up these reactions, we get more efficient reactions, and also we produce less chemical waste. So these catalysts are very, very essential for industry purposes. However, TPMA is not a perfect catalyst. We still are not getting 100% efficiency in a lot of reactions. And in fact, in certain ATRA reactions, we're only getting about 20 to 30% efficiency. So my research with Dr. Coyote Oshin really focuses on how can we make catalysts based on TPMA that are even more efficient. And so that's going to be what I'm going to talk to you a little bit about today. So TPMA is known as a transition metal catalyst, which means we have a metal center and surrounding by it are these big carbon rings. And for TPMA specifically, there are 3 carbon rings that have an iron center for copper 2 TPMA. However, these big carbon rings are very bulky. They take up a lot of space. So when this catalyst is going through these reactions, the active side of the catalyst, which is that little metal center, which is what actually helps make the reaction be more efficient, is often blocked by these big rings. There's catalyst in the solution that doesn't work as well as it should be because we have these big rings. So what my advisor and I, and by the way, you can see TPMA in figure 1 as seen on my screen. I'll see if I can highlight it. This is figure 1. This is the structure of TPMA. So you can see those big rings that I was talking about. So we are taking a molecule that is very similar called BPMA. It stands for bis-2-pyridylmethylamine. And we are seeing if we can make BPMA as effective as a catalyst as TPMA. But if you notice here on figure 2, BPMA only has 2 carbon rings. So by taking out one of those carbon rings, the active site of the catalyst, which would be a copper center right in the middle of BPMA, it doesn't show it in this image, but we would add a copper center to the center. Hopefully that active site would be more exposed, and therefore our reactions would be a lot more efficient. And so for the last couple of years, I've been working with Dr. Oshin to modify BPMA in various ways in order to make it as effective as TPMA. So the ones that I'm going to talk to you today are 2 catalysts that I synthesized called 3OH and 4OH copper 2 BPMA. And so what I essentially did was I took this BPMA ligand and I added a copper center to it. And then I also added this arm. And if you see, this arm is made out of 3 carbons, if you can see my mouse. If not, refer to figure 3. There are 3 carbons with that little OH group, which is represented by this red dot. And theoretically, we figured that this arm could attach to that metal center and detach to that metal center in order to allow for that arm to retract back and forth to expose the active site of the catalyst, but the molecule would still be happy being able to actually have the copper fully integrate with the two rings and the arm. And so I synthesized two catalysts, one with a 3-carbon arm and one with a 4-carbon arm that would theoretically have this arm open and close in the presence of a counter ion. And you could see that counter ion right here in figure 4. In this case, this is tetraphenylborate. And you can see these are X-ray crystallography structures of my synthesized 3OH catalyst. And you can see here we have the arm that is successfully not attached. And then we put it in the presence of a counter ion and it successfully attaches. So I synthesized these structures. We grew crystals out of them to run X-ray crystallography on these structures. And as you can see here, I just put in the 3OH copper 2 BPMA, but with the 4OH copper 2 BPMA, we saw the same retractability with the arm in the presence of a counter ion. So my advisor and I knew that we had successfully synthesized this catalyst and that it was doing what we wanted it to do. And now we had to see if it was as efficient as TPMA. And so I took my two catalysts that I synthesized. Remember, there's the 3-carbon arm and the 4-carbon arm. I took these two catalysts and I also took TPMA and we ran a whole bunch of reactions with them to see how efficient each of the reactions were, whether they had TPMA, the 3-carbon BPMA, or the 4-carbon BPMA. And if you refer to table 1, I ran a whole bunch of atom transfer radical additions using different alkenes, including 1 hexene, 1 octene, 1 decaene, styrene, and methyl acrylate. And I also ran a whole bunch of different catalyst loadings. And what a catalyst loading is, we really want only just a little bit of catalyst to make a reaction super efficient. We want to make things very inexpensive. We want as little catalyst as possible. So I tested a whole bunch of different catalyst concentrations going, and I think here I only show a 500 to 1 reaction, which means 1 mole of catalyst to 500 moles of reactants. But I ran a whole bunch of catalyst loadings all the way up to 100,000 moles of alkene to 1 mole of catalyst to see if my catalyst and if TPMA stayed as efficient as we reduced the amount we used. And as you can see in some of in these conversion percentages, which is essentially the efficiency of reaction that we saw, and we monitored this through proton NMR of the products we produced in these reactions, my catalysts, the copper 3OH BPMA and the copper 4OH BPMA, are almost as efficient, if not as efficient, as TPMA. And in fact, in certain reactions, including ones closer to room temperature, we saw my catalysts were actually greater efficiency than TPMA. And the other thing is that BPMA, the ligand that I synthesized my catalysts from, is actually more inexpensive than TPMA to make industrially. And so my results suggest a wonderful new alternative to TPMA that is as efficient, if not more efficient than TPMA in certain reactions, but is also less expensive to make. And so currently we are taking our results and submitting a manuscript for publication, hopefully to get these synthesized catalysts used industrially in ATRA reactions. And as I mentioned, we're focusing a lot on copper complexes. My future research is hopefully going to focus on iron complexes, which iron has a greater range of oxidation states, which is really important in catalysis. And hopefully we'll see as efficient, if not more efficient, results using an iron center. So yes, thank you so much. I really appreciate and have loved talking about my research. And yeah, have a great day. Let me quickly stop my recording. Goodbye.